I would like to introduce two more concepts, namely the notion of generalized momentum and the notion of cyclic coordinates. So the starting point is the Lagrange function, which depends on coordinates, velocities, and possibly may depend explicitly on time. And we define a quantity which we call generalized momentum, which is the following. We denote it by pi, and it's defined as the partial derivative of the Lagrangian with respect to the velocity qi dot. It's a generalized momentum associated with the generalized coordinate qi. Why is it called momentum? Well, let's check in Cartesian coordinates whether we recover the ordinary notion of momentum. In Cartesian coordinates, the Lagrangian, and let's stick to a single particle, is given by kinetic energy, which is mass over 2, and then velocity squared, minus the potential, which depends on position. And then we can consider this generalized momentum, dl over, which in this case is the partial with respect to xi dot. You see there's no contribution coming from the potential energy because that depends on position only. Just have a contribution from the kinetic energy. The derivative of xi dot squared is 2xi dot, and the two cancels, and you see what remains is mass times xi dot. So momentum equals mass times velocity, and that's precisely what we know to be the momentum. Yeah? So in the Cartesian case, this actually is the momentum, and for arbitrary coordinates, it doesn't necessarily correspond to the physical momentum, but it's defined in the same way, formally, and it's called the generalized momentum. Next, I would like to define the notion of a cyclic coordinate, and that is the following. If the Lagrangian does not depend on some of the coordinates, yeah? So let's say there exists a coordinate qk, a component qk, on which the Lagrangian does not depend. Then one says that this coordinate qk is cyclic. Yeah? That's simply the definition. But what is the consequence of that? If the Lagrangian does not depend on this coordinate qk, then let's look at the equation of motion we have here for the components k. That's what the equation of motion says. Well, if qk is cyclic, then the partial derivative of the Lagrangian with respect to this coordinate vanishes. This implies the left-hand side of this equation of motion is 0. And this implies that what is behind the time derivative must be a constant. So this implies that dl over dq dot k, that is a constant. But the partial derivative dl over qk dot, that's what we defined as the generalized momentum. Yeah? So this is nothing but pk, and we find that is constant. So a consequence of a coordinate being cyclic is that the associated generalized momentum is conserved. So we have a first conservation law. So the associated generalized momentum is conserved. Okay, I'd like to develop this formalism just a little bit more, so then you have the complete framework. And then after the break, in our last hour and tomorrow, we will look at a lot of examples where you will see all of that in practice. So one more concept I would like to introduce is the so-called Hamilton function. The Hamilton function is denoted by the letter h, and it's defined as the sum over all I, then the product of the generalized momentum pi times the velocity qi dot minus the Lagrange. So at this point it's just a formal definition, just like the Lagrange function itself and also the action. It's a mathematical definition, and it's at this point not yet clear whether it has a physical meaning, and if so, what the physical meaning is. But if we make sort of two rather innocent additional assumptions, then we can actually give the Hamilton function a physical meaning. Let's make two assumptions, two extra assumptions. The first assumption is that the coordinate transformation from Cartesian coordinates to our generalized coordinates, that this is not explicitly time dependent. So we focus on time independent coordinate transformations. And this excludes, in general, this excludes accelerating frames because they are characterized by the fact that coordinate transformations are time dependent. This has as a consequence, when we look at how the velocities are related, we find that the velocity in Cartesian coordinates, so xi dot, if the xi depends only on the generalized coordinates but not explicitly on time, then we can use the chain rule and write that as sum over all j partial dxi over dqj times qj dot. So the xi dot are linear combinations of the qj dot, where the coefficients, these partial derivatives, they don't depend on velocities, they only depend on position. And this has as a further consequence, when you look at the kinetic energy in Cartesian coordinates, this is, we know what it is, mass over 2, sum over I, xi dot squared. When we insert the previous result, we express the xi dot as a linear combination of the qj dot. Then we find that expressed in the new generalized coordinates, the kinetic energy is bilinear in the qj dot. So it has the form 1/2 sum over jk, and then we have from the first xi dot, we have partial xi with respect to qj. From the second xi dot, we have a partial xi with respect to qk. And then we have qj dot qk k dot. And we still have the mass somewhere. Let me squeeze in the mass here. There's an expression here in the sum in front of the qj dot and the qk dot. You can interpret that as a coefficient mjk, and that coefficient depends only on position. If at all, it depends on the position, but not on velocities. Because the xi, they are functions of the qi and not of the qi dot. When you take the partial, it's just a function of the qi. Yeah? So the mjk, this coefficient here, that depends, if it's not a constant, if it's not even a constant, it depends at most on the positions. And so in this sense, you say that the kinetic energy is bilinear in the velocities, the generalized velocities qi dot. Yeah? So they are this is bilinear in qi dot. So the kinetic energy is, that was the point of the exercise, the kinetic energy is bilinear in the velocities. And that's an important ingredient that we are going to need. And it's a consequence of the fact that coordinate transformation is time independent. Let's make a second assumption, which in a way is not really an extra assumption, but let me write it down anyway, that the potential as expressed as a function of the new coordinates, and the potential may possibly depend explicitly on time. Say if you have some driven system, or a system in a time-dependent external field, then the potential may depend explicitly on time. But what's important here is that it does not depend on the generalized velocities. If we start from the observation that the potential does not depend on velocity in the Cartesian description, then it won't depend on velocity in the generalized coordinates either. But I still want to write it down explicitly that this is not velocity dependent. Then if we combine these two assumptions and we look at the generalized momentum, remember that the generalized momentum is the partial derivative of the Lagrange function with respect to the velocity, qi dot. The Lagrangian is kinetic energy minus potential energy, but the potential energy doesn't depend on velocity. So only the kinetic energy contributes here. So in fact, we have, this is the partial of kinetic energy with respect to velocity, qi dot. But then we use the fact that the kinetic energy is bilinear in the velocities. So it has this structure as noted above, 1/2, then the sum jk, some coefficient mjk, which depends only on position, and then the velocities, qj dot and qk dot. And when you insert that bilinear form here, you find that the generalized momentum is given by the sum over j, mij, the coefficient mij, times velocity component qj dot. Now we can insert this form for the generalized momentum into the definition above of the Hamilton function. The first term, the sum over I, pi, qi dot, now acquires the form, it's a sum over ij, the coefficient mij, and then the velocities qj dot, qi dot. Yet this sum is nothing but 2 times the kinetic energy. When we use this result and insert this into the definition of the Hamiltonian, what remains is the Hamilton function is 2 times the kinetic energy minus the Lagrange function, but the Lagrange function in turn is defined as the difference of kinetic energy and potential energy. Taken together, what remains is that the Hamilton function equals the kinetic energy plus the potential energy. Which is nothing but the total mechanical energy. So we see that if we make these 2 assumptions spelled out above, then the Hamilton function can be given a physical interpretation, namely the total mechanical energy. If, on the other hand, the 2 assumptions above are not justified, then in general the Hamilton function is just abstractly defined as above and does not necessarily have a physical meaning. With this definition of the Hamilton function, we can look at another conservation law, namely the conservation of this Hamilton function, which, if the Hamilton function can be identified with the total mechanical energy, is tantamount to energy conservation. Let's look at the change in time of the Hamilton function. First, we insert the definition of the Hamilton function. Then, using the product rule, we find 3 contributions to the total time derivative of the Hamilton function. It's the sum over I pi dot qi dot, the sum over I pi qi double dot, and then we have minus the total time derivative of the Lagrange function. Let's have a closer look at the last of these 3 terms, the total time derivative of the Lagrange function. There are 3 contributions to this total time derivative. The Lagrange function may depend on the generalized coordinates, the generalized velocities, and possibly it may depend explicitly on time. Accordingly, there are 3 terms contributing to the total time derivative. There's one term with all the partial derivatives with respect to the generalized coordinates, multiplied with the associated velocities. Then there's a contribution with partial derivatives with respect to the generalized velocities, multiplied with the time derivative of these velocities, i.e. qi double dot. And finally, there can be a contribution if the Lagrange function is explicitly time dependent of the form partial derivative of L with respect to time. The partial derivative of the Lagrange function with respect to a generalized coordinate, that can be expressed with the help of the Euler-Lagrange equation as the time derivative of the associated generalized momentum. The partial derivative of the Lagrange function with respect to a generalized velocity is, by definition, equal to a generalized momentum. Now we recognize that some of the terms in the expression for dH over dt cancel. The sum over I pi dot qi dot we have both on the first line and on the second line, with different signs contributing. So they cancel. Likewise, we have the sum over I pi qi double dot. These terms too cancel. What remains is that the total time derivative of the Hamilton function with respect to time is given by minus the partial derivative of the Lagrange function with respect to time. This implies that as long as the Lagrange function is not explicitly time dependent, and therefore its partial derivative with respect to time vanishes, the Hamilton function is a constant of the motion. Its total time derivative vanishes. And if in addition the extra assumptions that we made on the previous page hold, so that the Hamilton function can be identified with the physical total mechanical energy, then this result is equivalent to energy conservation. Let us return to our earlier example of an inclined plane. So we have a mass gliding without friction on a plane that is inclined with respect to the x-axis by an angle alpha. We chose as the generalized coordinate the distance of the mass from the origin, and this generalized coordinate is related to the Cartesian coordinates x and y by the coordinate transformation that you see on the right-hand side. This coordinate transformation is time independent, so the first prerequisite for identifying the Hamilton function with the total mechanical energy is satisfied. The potential energy depends on the generalized coordinate only. It's given by mass times gravitational acceleration times the generalized coordinate s times the sine of the inclination angle. It does not depend on the velocity s dot. So the second prerequisite too is satisfied. Therefore, we can identify the Hamilton function with the total mechanical energy. Let's now calculate the Hamilton function. Knowing that it equals the total mechanical energy, we can simply write the Hamilton function as kinetic energy plus potential energy. For both kinetic and potential energy, we already have a formula, and we can simply insert the known results. The Lagrange function we had already calculated, and we had found that the Lagrange function is a function of the coordinate s and the velocity s dot only. It does not depend explicitly on time. As we just learned, this implies that the total time derivative of the Hamilton function vanishes. Therefore, the Hamilton function, which equals the total mechanical energy, is conserved.